Welcome to a deep dive into the world of artificial intelligence, where we uncover the magic behind machines that can see. Today, we're exploring convolutional neural networks, or CNNs, the true backbone of modern computer vision. These powerful algorithms have revolutionized how computers understand and interpret images, from recognizing faces on your phone to enabling self-driving cars. Before CNNs, teaching a computer to identify even simple objects was an immense challenge. Traditional methods often relied on handcrafted features, which were brittle and couldn't generalize well. Imagine trying to program every possible variation of an object. CNNs offer a fundamentally different, data-driven approach, learning features directly from the images themselves. At its heart, a CNN is a specialized type of neural network designed to process data that has a known grid-like topology, such as image pixels arranged in a 2D grid. Unlike a fully connected neural network where every neuron connects to every other neuron in the next layer, CNNs employ a more structured and localized connectivity pattern. The cornerstone of any CNN is the convolutional layer. This is where the network performs its primary feature extraction. It uses small matrices, called filters or kernels, to scan over the input image. Think of these filters as tiny magnifying glasses, each designed to detect a specific pattern, like an edge, a corner, or a particular texture. The convolution operation itself works by sliding a filter across the input image, pixel by pixel. At each position, it performs an element-wise multiplication between the filter and the corresponding patch of the image, then sums up the results to produce a single output pixel. This process creates a feature map, highlighting where the detected pattern appears in the original image. Multiple filters are typically used in a single convolutional layer, each learning to identify a different feature. For instance, one filter might detect horizontal edges, another vertical edges, and yet another might respond to a specific color gradient. As the network trains, these filters automatically learn the most relevant patterns for the task at hand. Following the convolution, an activation function is usually applied to the feature map. Rectified linear unit, or ReLU, is a common choice. It introduces nonlinearity, allowing the network to learn more complex relationships in the data. Without nonlinear activation functions, a CNN would simply be a linear transformation, unable to capture intricate patterns. Next in line is often the pooling layer. Its main purpose is to reduce the spatial dimensions of the feature map, thereby decreasing the computational load and the number of parameters. This downsampling also helps make the detected features more robust to slight shifts or distortions in the input image, a property known as translation invariance. There are several types of pooling, with max pooling being the most popular. In max pooling, the input feature map is divided into non-overlapping regions, and for each region, only the maximum value is taken as the output. This effectively summarizes the presence of a feature within a region, discarding less important information. A typical CNN architecture consists of several alternating convolutional and pooling layers, gradually extracting higher-level features and reducing the data's dimensionality. After these layers, the output is often flattened and fed into one or more fully connected layers, similar to a traditional neural network, which then perform the final classification or regression task. The applications of CNNs are vast and impactful. They power image classification systems that can categorize millions of images, object detection algorithms that locate and identify multiple objects within a single image, and even semantic segmentation, which labels every pixel in an image with its corresponding object class. In essence, CNNs have provided computers with the ability to perceive and understand the visual world in a way that was once thought impossible. By automatically learning hierarchical features directly from data, they've unlocked unprecedented capabilities in fields ranging from medical imaging to autonomous navigation, continuing to push the boundaries of artificial intelligence.